All right, so next speaker is Vit Sriprachyakul, and he'll tell us about strings near the boundary of AdS3.
Thank you very much. So let me thank the organizers for this wonderful workshop and also for giving me the opportunity to speak. So I would like to talk about some recent development in AdS3 CFT2, which I've done with these collaborators. So as you know, AdS-CFT relates string theory in anti-de Sitter space-time to conformal field theory living on the boundary of that AdS space-time. And so the feature that makes AdS-CFT interesting is the so-called strong-weak nature of AdS-CFT. But unfortunately, it's also the feature that makes it extremely hard to prove rigorously. So the strong-weak nature of AdS-CFT is the following. So if you start with string theory in anti-de Sitter, string theory, AdS-CFT says that the due CFT to this string theory is a weakly coupled CFT. And so you can do all sorts of perturbative analysis here and then deduce some behavior on the string theory side. And now if you crank up this coupling on the due CFT and then you enter the strongly coupled regime, now perturbative analysis is not so useful anymore, but then AdS-CFT says that the due gravitational theory is well approximated by the low energy approximation of string theory, namely the supergravity approximation of string theory, and therefore you can infer the behavior of strongly coupled CFT by studying essentially classical supergravity situation. But in this talk, I'm going to tell you about one limit on the worldsheet theory which you could take, which then simplifies a lot of calculations on the worldsheet theory. In particular, it allows you to calculate explicitly worldsheet amplitudes or SMATCs, and then we can use that information to deduce or actually derive the due to the CFT. So this limit that I'm talking about is the so-called near boundary limit, which I'm going to talk more about how we define such a limit on the next slide. But let me finish this slide by quickly mentioning that there is one other limit in which we also have sufficient analytical control on both the AdS string theory and the due CFT side, so much so that we actually have a perturbative proof of AdS-CFT in this particular limit, and that's the so-called tensionless limit in type 2b string in AdS3 times S3 times 2,4. And this is the work pioneered by these people. All right, so let's go back to the near boundary limit. So we start as usual by writing down the string theory that describes strings moving in AdS3 times some compact directions, and the compact direction I denote by x. And then I will assume throughout this talk that this background is supported purely by NS and S flux, so I do not turn on any Riemann flux at all. And then in going to the near boundary limit, we simply say, okay, when we calculate worldsheet amplitudes, we're going to keep only the contribution that comes from the worldsheet that look like this. So here, the blue line represents the worldsheet, and the black line represents the conformal boundary of AdS3. So as you can see, we focus only on the contribution that comes from the worldsheet that lives near the conformal boundary of AdS3, and that's why we call this limit the near boundary limit. And also I should mention that this configuration of the worldsheet is also known in the literature as worldsheet instanton, as was discussed already by Modesina and Iguri in 2000. And so it turns out that by focusing on this kind of contribution, one can actually compute worldsheet amplitudes to any number of insertions. So what we computed was amplitudes of ground state with the worldsheet of genus 0 using the path integral formalism. And then this information allowed us to deduce the due to the CFT. And so let's talk about the main result of this near boundary consideration. So if you first start by considering bosonic string in AdS3 times x, again, x is the compact directions, it turns out that the near boundary limit predicts that the due CFT in this case is a symmetric orbifold whose seed theory is a linear dilaton theory tensored with these compact directions. So these compact directions are exactly the same ones that appears on the worldsheet. And then you deform the symmetric orbifold by a marginal twist to deformation. So that's the prediction that comes from this near boundary consideration. Now, I want to mention that we were not the first one to come up with this duality. It was already proposed by Lorenz Eberhard in 2021, but there in that paper he only considered 2 and 3 point amplitudes in the worldsheet. So in a sense, our near boundary limit work extends the range of validity of this bosonic duality up to any number of insertions. Right. And so at this point, one could ask, what happens if we add supersymmetry to the game? And it turns out that by bidding up on the bosonic result, one can actually compute some 3 and 4 point functions in superstring theory. In this background, AdS3 times, again, some compact direction, where here I assume that the compact direction has at least n equals 1 supersymmetry. Right, so by computing those 3 and 4 point functions, the result is that the GCFT is given by this deformed symmetric orbifold. So it's a symmetric orbifold of now an n equals 1 linear dilaton times, again, the compact directions that appear on the worldsheet, and then possibly deformed by some marginal twist to deformation. Right. So there are 2 points that I would like to emphasize for this supersymmetric proposal. First is that the proposed duality is valid for any consistent background. And when I say consistent, I mean that this compact directions has to satisfy the string radicality. So the central charge of AdS3 plus that of x has to be 15. But apart from this condition, this proposal should work without any other constraints. And the second point that I would like to mention is that this proposal is for any amount of NSNS flux. In particular, we're not in the tensionless limit here. So the NSNS flux on the worldsheet could be any value. All right, so let me finish by giving you some outlook. As I said in the last slide, because this proposal is completely generic, we can plug in some interesting compactifications. In this case, I plug in x equals S3 times S3 times S1. And then the near boundary limit predicts that the GCFT in this case is given by this deformed symmetric orbifold. Now, it would be good to check this duality beyond the level of near boundary consideration. But there's one instance where we have checked it quite extensively. And this is what Matthias talked about in the second half of his talk in New York. This is the so-called tensionless limit of strings in AdS3 times S3 times S3 times S1. So by tensionless, I mean you take the supersymmetric level of the SU2 Westerminer-Witten model on the two S3s to be 2, and then that implies that the supersymmetric level on the AdS3 is actually 1. And then in this case, the C theory simplifies, and you have just these free fields. So you have 8 free fermions plus 2 bosons, 1 compact and 1 non-compact. And then we can also argue that there is no need to turn on the sigma 2 marginal deformation here. So in a sense, the GCFT is a free CFT. So this is the work in progress with Matthias, and hopefully it will appear on arXiv soon. And so with that, I conclude my talk here. Thank you.
Yeah.
Okay, yeah. So AdS3 by itself is dual to a CFT2, right?
Yeah.
And could you comment on this near boundary limit strictly from the CFT? So what limit am I taking of the boundary CFT to extract the near boundary limit?
That's good. So actually, this limit concerns mainly on the worldsheet. So you take the limit on the worldsheet. Yeah, and then you.
Well, I'm basically asking what's the CFT spacetime interpretation of that procedure. So you did something on the worldsheet. I understand that.
Yeah.
The thing is, like, if that is a limit of a, like, if it's a well-defined scaling limit of a system, they should have a target space interpretation. And I'm wondering what that is.
So when you say target space, you mean target space on the worldsheet, or you mean the GCFT? Like when you say.
Well, so basically the way I think about it is that string theory and AdS, the target space is the CFT, right? Like the space-time content of the target space theory is the dual CFT. Well, dual CFT is equivalent to the target space, so those are the same thing. Am I not making sense? Sorry.
Yeah, I'm not sure I understand your question, but also there is one point that I want to mention here, which is the fact that this UCFT, we only know how to define it perturbatively. Like we don't, so I mean, we only know how to define it perturbatively in this deformation.
That's fine. The statement is whatever the new boundary limit of the full target space CFD is, it's a deformation of that symmetrical. That statement I understand. What I wanted to understand was what was the physical meaning of taking the new boundary limit in the first place. But
You mean from the target space point of view?
From a dual CFD point of view. Is it a scale? Can I think of it as a scaling limit, or are we shoving this issue under the rug right now?
Yeah, I mean this I'm not sure. I haven't thought about it. As I said, I only have the intuition from the worksheet, but yeah, from the dual CFT point of view, yeah, I'm not really sure.
Okay, well, really about that. Thank you.
So how does this proposal work for the tensile string case where you have k equals 1 on
No.
3 equals 4? Because there we don't have this continuum. So
Sorry, what was the question?
you said that this proposal works for any k. I mean, but
Yep.
for k equals 1, we know that we don't have this continuum. I mean, so
Right.
So how does that match?
Yeah. So okay. So there was some argument to get from this generic k to k equals to 1. So if you plug in x equals s3 times t4, then this becomes n equals to 1 linear dilaton times SU2 times t4, right? In fact, this specific background S3 times T4 was also discussed in this 21 paper by Lorenzo Bahar. And what he proposed was that you should think of the n equals 1 linear dilaton together with the SU2 as n equals 4 linear dilaton. And for k equals to 1, the central charge of that part is 0. So he argued that that should be a trivial theory, and therefore you get a symmetric orbital of T4. Also, because you have the continuum, the bottom of the continuum, you can also argue that there is no twist to marginal deformation, and therefore you get a free symmetric of T4 in that case.
Any other questions? If not, let's thank Vit again.